We are recording. We are recording. Cool. So it's been a while, but finally, chapter 22. I believe at this point the latest video is chapter 20. And we still have two Karuta recordings to put on there. So this is gonna take a while to be on YouTube.
Yep.
Cool. So last chapter we talked about monads in programming, and now we're gonna talk about its counterpart, which is monads in category theory. And we're gonna reach the famous meme, which I think is worthwhile. So we will have a better understanding on what this means.
Yep.
Monad is just a monoid in the category of endo functors.
Classic Haskell meme.
Yeah, this is a very classic. So let us just start. So he starts the chapter. He starts the chapter by basically talking about expressions, right? So we have an algebraic expression such as this one. And then he talks about that we can rewrite this as a diagram, which is very, very, again, if you ever did any sort of toy programming language, this is not uncommon to see around, or even in math for that matter, that you can visualize these type of expressions as trees. And then we're gonna do, and all of this chapter is a kind of like intuition, so it's just hand waving argument, so don't take this as a proof. But what we're gonna do, we will try to interpret monads as a process of applying a substitution process on an expression.
Which is a very general thing, we should say.
Yeah, substitution is a very general thing, that's fair. So as an example, if you pick this expression and you swap x by y minus 1, you're gonna get this thing, right? You're gonna get this thing. So let's suppose that you took an expression of type MA, in which M is the monad, and apply a transformation of this type, right? So you're going to replace every single instance of A with an MB. The result is an expression of type MB, right? That makes sense. That
Yep.
so you're going to have, this is what you have. This is the function that you have, and this is going to be the output result. And if you take a look at it, you're going to see that this is the signature of the monadic mind, right? Of course, that this is there is a jump here because if you just do literally what he said, you're gonna have an M of B. You're gonna have two M's, right? But it is not by a coincidence that we're gonna start this discussion talking about join, because join is the function that will get around this problem of accumulating M's, let's say.
Yep.
So let's get to the math of it right now. So we are gonna use different letters. So we're gonna use I forgot the name of the Greek letters.
That's Micron, and the other one is Eta, I think.
Makes sense. So join and return are polymorphic functions. We're gonna see what they do very shortly. So a monad is defined as an endofunctor T equipped with a pair of natural transformations mi and eta, which are just renamings of join and return. And what does mi does? What does mi do? It picks a square of the functor, so again m of m, and put it back to m, put it back to t. We are basically solving the problem that I just foreshadowed, right? So if you just replace a in here using this function, you're gonna have an m and of a. But if you apply me, you're gonna get m of a only, right? So this has this notation here, so you just compress the composition with a square. Yeah, and we can only do this kind of squaring with the functors. Makes sense?
Yeah, because otherwise you can't put the outputs of one functor as the inputs to the next one, right?
Mm-hmm. Mm-hmm. Otherwise, if that was not the case, monads would compose, right? In general, the general case.
Uh, I don't think so, actually.
I do think so. If this was not t, was another functor, let's say
No, no.
g.
If the point, no, the point here is it needs to be an endofunctor. That means it needs to go from a category to itself.
Yeah, no, but that makes sense. But but we are elaborating on why this needs to be the case to do this kind of squaring. Why this is
Because
always true for for any functor t.
because if a functor takes a category and goes to that same category, you can then take the output of the functor and call the functor again with the same value,
No,
right?
that is correct. But then, um,
If t was
why?
not an endofunctor,
Yes.
that would be like taking a function from a to b and try to compose it with itself. It's not going to work unless a and b are the same.
Oh wait, repeat the answer to that.
Like if you have function from a to b, you
Hmm.
can only compose that function with itself if a and b are actually the same.
Oh, that is correct. Actually, that is correct.
That
That is correct. Uh, yeah, no. So what I said doesn't apply here. Even if that was not this cannot be an endofunctor because the types would just not match, right?
an endofunctor would be the case of a and b are the same because a and
No,
b,
yeah,
like
but
by definition, yeah.
assuming that A and B are different of what you said. Cool. So this is join, and as we already said, this is this me in the Greek letter, and the component of this transformation at an object T is this thing. So again, m of A goes to m of A. This is join. Then we go to eta, which is basically return, which is basically peer, right? So you have the identity functor going to the functor, the target functor.
Yep.
In this particular case, if you apply to an element A, it's going to do this, which is return. And then now we're going to go back to Kleisli categories because about going back to the fish. And you can actually implement the fish, which is being used this notation, using this thing. And if you look at the types, we are starting with F and ending up with this, which means that, well, it's me applied to C, which means that this is going to be TC, TTC going to TC, right?
Yep.
Which means that you are starting from A and going to TC at the end of the day.
Yep.
And then we go to the Haskell notation of that. So this is just a one-to-one mapping. T is a functor, so F map there, F, and this is just join. So there it is. Here's the fish. And you can
And for
also
and
go.
the arguments are backwards because this is from left to right, but the circle dot is from right to left.
Yeah, and if
Yeah.
you want to go, instead of doing point-free notation, this is how you would do it. Cool.
I don't
Uh,
know why you would do it like that. The one above is clearly better.
the Haskell community is kind of divided in terms of point-free notation. Like, have you ever heard the? There is a name. Um,
Oh, you're gonna
mm,
bring up the owl thingy, right?
no, but yeah, the owl is just. But it is not. It is the owl is the implementation of this guy, but this guy has a name, and I'm not remembering the name. Cool. Yes, but if you at the point, okay, so just for recording purposes, what I'm talking about. So what is this operator? It has a name that I just forgot, but the implementation of it is this thing, right? So there is an equal here. When you reach this point of point free, you should ask yourself what the heck we're doing.
Or you could switch to APL.
That's fair. That's very fair. But if you reach this guy, that's when the point free notation starts to get a little bit sus. Anyway, so the Clariers form a category. To form a category, we want their composition to be associative. and the eta at A to be the identity class error at A. This requirement can be translated to monadic loss, as we already saw, right? But there's another way of deriving this loss where they look like monoid loss. So the me is gonna turn to multiplication, and eta is gonna be the unit.
Can I just say, this chapter, things we're about to see, they remind me a lot of when I read about generalized arrows.
Generalized arrows. I don't remember reading about that actually.
I posted a paper on the server a while back. I don't remember when, but it's been a while actually. I can dig it up and we can take a look later, but it's very long, so
I
not really.
understand. Uh, so roughly speaking, the associativity law states that there are two ways of reducing the cube of t. So if you have a t composed with t, like you just like a series of composing the functors, the on the functor, down to t, it must give the same result, which makes sense. It's associativity, right? So kind of makes sense. Two
Essentially, yes.
two unit laws, left and right, state that eta is applied to t and then reduced to by me, we get back to t. So what does this mean? Um, I think there's a drawing. Yeah, this one.
Yeah, yeah.
So if you apply eta after t, oh, there is the confusion again. The
No,
notation. There is a confusion on
no,
notation this again.
no
Uh,
risk of confusion.
yeah, so let's completely read it and then go back to the drawing down there. So things are a little tricky because you're composing network transformations and functors. So a little reflection on horizontal composition is in order. For instance, T3 can be seen as composition of T after T square. Um, we can apply to it the horizontal composition of network transformations. So basically, uh, I don't really remember why the name is horizontal, but if you have a member in the C category and then you compose T square and you apply that to it, you're gonna go back to C anyway because this is an endofunctor. And if you apply T again, you're gonna go to C again, but now you apply T 3 times. And what we are saying basically is that if you pick T square and you apply me, which is join, you're gonna have another transformation down here, which is just T. And if you have T and you apply the identity functor to it, you're gonna have T again.
That's
And
actually the identity natural transformation, not the identity functor.
the identity.
Yeah, because T is a
Oh no,
functor,
it
you're
is that.
applying.
Sorry.
Yeah,
IT is the identity transformation from T to T. Sorry, that is true. Well, it needs to be an natural transformation, right? Because otherwise it would not be the case. But if you're going from a functor to a functor, this needs to be a natural transformation. Makes sense. Anyway, so what you're basically saying is that these things go to the same place. These
yep.
things, which means, uh, which kind of means that composing this is the same as just going to T. So if you do identity natural transformation from T to T, after you did me, that means that you're going from T squared to T. So you often see this notation for this type of horizontal composition, and then this is the notation problem.
No risk of
And then,
confusion.
then the argument is that it cannot be bad because it makes no sense to compose a function with a natural transformation, which is kind of, well, I wouldn't say it's not fair. It is just unnecessary.
It
Uh,
would be a type error otherwise.
yeah, yeah. We can also do this diagram here. So this is the thing. So if you have a T3 and you do me T, well, identity after me,
Have, yeah.
you're gonna go to T squared. And if you apply this again, you're gonna go to T.
And then there's the rest of the square.
And alternatively, we can treat T3 as a composition of T2 and T and apply me after identity to it. So if you grab this, right, T3, and you apply identity, you're gonna get T3. But if you apply me, you're gonna get T2, which is the same as this thing. which can be reduced again by using me again. So it's kind of
Yeah,
like it's a double join. We
yeah.
require that
Basically,
the two pa okay, go.
yeah. No, this square, basically this square needs to commute, right?
Yeah,
You need to actually end up in the same place, regardless of which path you choose.
yeah. Yeah, but this one is kind of obvious, I would say, because you are just using the identity net transformation, so it would be kind of insane if this is not the case.
But me
Um,
could be wrong, right?
how could me be wrong though?
That's a good question. I'm not sure.
Yeah, so this is kind of like out of the whole commutativity squares that we have seen so far, this one is not that surprising in my opinion. We can apply the horizontal composition now using the other guy, right? So this is just uh, join. Now I need to talk about return. So if you apply eta after identity to the composition of the identity functor after t, so if you apply this after t, you're gonna get t. And if you apply this thing to it, you're gonna get identity again. So t, but n, not n, eta is
Turning the
is
identity to another t, so now it's t squared because it's two of them.
no wait, but I said it wrong though. To the composition of the identity functor after t,
I after t.
I after t. So t is the first one, right?
Yeah.
So you have the first one, you apply identity, which does nothing, right? So you have just t.
By itself, yeah. If
And
and if you apply
and if you
and then
apply
if you
that to
apply
this, which is identity, so you have t again, you're just gonna apply eta. And eta,
eta to identity turns it into t.
um, actually the answer is t squared, right? Yes. So the thing is, after all of this process, you're gonna have t, but because eta produces another t on top of it, you're gonna have t squared.
That's not quite it, but okay.
I don't understand how that's not quite it.
Because
It's what's here.
you're applying a horizontal composition. So you're applying eta to the identity, right? Which gives you t.
But we don't have an identity. That's my confusion there.
You do. It's an identity of I after t. Look at the diagram.
You have an I after T.
Yep.
You have
That
an I
paragraph is
after
talking about
T.
that green arrow from that I after t to the t squared in the middle.
This is not green, dude. Sorry to tell you that part.
Ah, I'm using red shifts. That's actually blue, right?
Yeah. Um, that's kind of. Yeah, I am actually pretty confused, and I understood this earlier. So I is a functor in this case.
It is a functor,
It is a
yes.
functor. So this is the identity functor.
And if you apply eta, the natural transformation eta to it, it becomes a t.
Yeah, but that's not what we have. We don't have an I. We don't have I. We have I after T.
And you are applying a horizontal composition of eta
No, but the
after
result of this
identity.
is just T.
It is, but if you apply the natural transformation eta after identity, that becomes a t squared.
No, that part I understand, but you said that's not quite it before. That's what I'm trying to understand.
Go down a little bit to the there, yeah, there.
Hmm.
Basically, he's basically saying, okay, you have identity from C to C, and then at T, or actually it's backwards, right? It's I after T, so it's T and then I as the natural transformations here. Not natural transformation, the functors, the end of functors. And
Hmm.
then he's basically saying you're applying the eta instead of B to the identity functor, which becomes a T.
Yeah, there's something missing, man. Because this is just T. This is just T,
It is, yes.
which means that I am picking T and apply putting on the right of this. This is identity natural transformation. So it also does
No, no,
nothing.
no, no. That would be just well.
No risk of confusion.
Well, I suppose technically that is also correct because these are just two compositions with identity, right?
Yeah.
Because that T in the natural transformation is actually identity, right?
Yeah, this is just IT, which is identity natural transformation. This. So this also does nothing, which means that we have eta and t. And then it comes the
Yeah,
question. Uh, the type signatures are kind of weird because we can't have a t.
it's not a T. It's
But you just said yes 10 seconds ago.
no, no,
What?
no, 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 no. Look, you have I after T, which yes, if you take it as a single object, then yes, that's equivalent to T. But that's not what it's treating it as. It's treating it as actually the composition I after T because it's interested in the components of the composition.
Yeah, I'm
Just
having a hard time understanding how this what you said though. Because to
just
me this is
stare
just type not checked at all. This
just
is expecting an
stare
I and we don't have an I.
we have an I.
We don't.
We
This is
do.
this is just T.
This is I after T actually.
Yes, it is I after T. But what is the result of this composition? T.
You're talking about actually evaluating the composition, Lemos. That's not what it's doing.
You're saying I am evaluating the composition. I don't understand. I don't understand. This is identity, so I can cut this. And because this T is not the same as this one. This is a functor, this is another transformation. Then I have eta being applied to this thing, and this thing is T. So I'm applying eta to
That's
T.
that's not how that's not how horizontal composition works, Lemos.
But that's exactly what we did before. I am missing something. I am missing something. The result should be the same as if we apply the natural transformation directly to T. Yeah, so what's basically saying is, like, discard all of my confusion. We're gonna go from this to this, which actually makes sense, but the types to me just does they don't check. But it makes sense to go to T square because eta is just adding another wrapper, and then you can reduce that to T again by using me, which makes sense. And you should also get the same by like reversing them. So if you have identity, if you have T after identity, and then you apply this thing, you're also gonna get the same
Identity,
result, and then you're
yeah,
gonna have
identity after eta.
this is not identity after. Oh, identity after eta here in the blue one. Yeah, that's
Yeah,
correct. So yeah, so aside from the types that to me are not checking, this makes sense. But what am I missing here? Because you said that I cannot evaluate this thing.
because there's a difference between there are two ways to compose natural transformations, right? We're talking about the weird one here.
Yeah, but I don't remember the weird one that well. That's the problem.
Don't worry about it. You can reread the chapter later.
That's the problem. No, but then the types not will not check here for me.
They do. If you scroll up a little bit, there's
So
an
scroll up.
example of that. Yeah, there.
Where? Exactly.
That diagram, that's the thing.
This diagram. You're talking about
Yeah.
composing the vertical arrows.
Basically, we're talking about applying the horizontal. This here is applying the horizontal composition of I after me to the to the functor composition T after T square
Yeah,
in this
I
case.
remember this nonsense. These are vertical arrows, but we call this horizontal. I
Yeah,
remember
the thing
this.
below is the same thing except you replace I after T after me with eta after I, and you replace T after T squared with I after T, basically.
Wait, you said a lot of letters in there. Let's go back to here. So which one I replace? Let's start from this t square here.
Yeah, you basically replace that t square with I, the
Okay.
identity functor,
Okay.
and you replace the me with eta.
Uh, what's in the bottom here?
Uh, Stays the same actually.
So you have I here, which is the identity functor, and you're telling me that instead of me, it's eta here.
Yes,
Well, that makes sense. That's the type signature of the guy. That makes sense. Now, and what's on the right here?
it actually stays the same.
Stays the same. So you're telling me that we are composing eta and this guy.
Yeah,
And this guy is also t here, t here.
yes,
So we have I here, t here, t here, t here, eta, and identity.
yes.
And the composition is eta, eta after identity?
This would be identity after eta, which is the same, which is the immediate follow-up. But yeah,
You said identity after the eta, so it's this one.
yeah.
Ah.
The other one is the same. It's just flipping the order around, right?
Yeah, no, if you flip this, you're gonna get the same. Yeah, that helped. That helped. That helped. Thank you, Marinho.
You're welcome.
Okay, cool. So, and then that's basically establishing what and why. Let us explain where are the similarities, right? The similarities between a monad and a monoid are striking. You have multiplication me unit eta
Eta.
associativity and unit loss, but our definition of monoid is too narrow to describe a monad as a monoid. Okay, so let's go back and try to explain why they are so similar. Where are the similarities? Eta is basically working as the mempty, right? As far as I can tell.
Eta is basically working as the empty.
Yeah, unit.
Basically, yeah.
Because
Um,
yeah, because if you like, this is a stretch. Well, this entire chapter is a stretch, but we can stretch it even more. If you assume that eta is the mempty, it means it doesn't matter, which means that t, well, the identity will also doesn't matter because it's the identity functor or the identity
natural
uh,
transformation.
natural summation, right? So you wait, wait.
Well, actually, in this case, it would be the identity functor necessarily, because otherwise you can't apply eta to it.
No, yeah, no, that makes sense. But that my understanding is that the unit of eta is that this is the neutral element, right?
Yeah, because it maps to it maps from identity, I should say, right?
It maps from identity. You mean eta?
From the identity. Yeah, it goes from the identity to t, right?
Yes, it goes from identity to t. But why are we getting t square? Oh, because of this t.
Because of this t that was already there, yes.
Yes, okay. So, ouch. Okay, so how can we explain that they are similar? Jeez. Okay, this diagram is the associativity as well. This
Yeah,
is the
basically.
associativity. Cool. The multiplication, it's saying it's me.
It's the one that
Uh,
actually takes the square to a single thing.
yeah, but I'm having a hard time explaining. Wait, to my head, it is similar, but how to explain that? Let's generalize the notion of the monoid. Do you think we can try more, or should we go further?
Let's go further because it will become clearer as we go. I
Okay,
think.
we think. So let's go back to the conventional definition. So this is the conventional definition. So the binary operation append must be associative and unital. Multiplication by the unit empty is a non-opt. Uh, sure. Okay, so yeah, if you multiply by the unit empty is a non-operation. You're just gonna go back to where you started.
Yup. You can multiply by 1 as many times as you want. You'll never leave where you started.
Yeah, but I have a feeling that this is written in here, but I cannot explain. Because you have a t and you're going to t again. So it is kind of here, but in Haskell definition of append is curved. Yeah, so it can be interpreted as mapping every element of M to a function. We've seen this before. In this
Yup.
interpretation, that gives rise to the definition of a monoid as a single object category where endomorphisms represent the elements of the monoid. But because curving is built in, we could as well have started with the definition of multiplication. So this is uncurving this thing, and now we
Yup.
are mapping a pair of objects to another one, to a single one.
Yup.
So now we have pairs, makes sense. Replacing, and now we have a different suggestion of generalization, which is replacing the Cartesian product with Cartesian product. We could start with a category where products are globally defined, pick an object M there, and define multiplication as a morphism. Yeah. So just for the sake of explanation, we are using very loose notation. So because sometimes this is mappend, but we are calling it multiplication. And this is
Yeah.
empty, but we are calling it unit.
Yes.
So that's kind of important. And that's why that's the bridge that you need to make when reading this thing. So the multiplication me should be mappend. Should be mappend. Um, should be mappend. And if you think about it, it kind of makes sense because you have two things, right? Two things, two
You have,
things,
you have a pair, basically.
and you are
Not
going
really,
to a
but
single one via me.
yeah.
And
Yeah.
uh, in here, you are going from t to not to t again, and you pass through eta and it didn't matter. So it's kind of that's how I see it at least. Uh, but anyway, let's continue. So we have a problem. Is in an arbitrary category we can pick inside an object. How do we pick the unit element, right? So there is a trick, which again is using the singleton set. So we are basically going to implement a function that, given a value of unit type, it will return us empty. The singleton is a terminal object in set, so it's natural to generalize the definition for any category. So this is now the new eta. This is now the new eta.
Yep. Takes the terminal object, returns M.
Exactly. So and that there's a difference between that eta and this one, right? So this one is terminal object, and then the element. So you need to try to see the parallels in there. So cool. Unlike our previous definition of a monoid as a single object category, monoidal laws are not automatically satisfied. We have to impose them. Uh, so let's formulate them to establish the monoidal structure. So we start with the associativity. In Haskell, and again, we're going to work now with pairs. We're going to work now with pairs. So we want to establish this. This is an instance of associativity working. So you have the thing working on this and then working with x out with the result of this. And associativity means that you can actually do the x with the y first and then doing with the z. Then to do this, we're going to actually use the bifunctor. We're going to actually use the bifunctor. Because if you want to write this operation in a point-free way, you're going to end up with this thing. So what is this doing? There is a compose here, so we're going to read this first. We're going to bimap identity to x and the mu operation to the pair, and then we're going to compose the result of that with another mu. So that's exactly what is happening in here. And then we can also apply the same procedure to the right side, which is going to end up with this. The problem is that this is this, right? Well, this and this, we want to put an equal between them, but we can't because they're actually with an instance, which is this thing and this thing. We can't make them point free because these two things are not isomorphic. right? So this is not the same as this. So we can't write this thing. But there is a way to make it, which is to write a helper function that just rep, replaces where the parentheses are, like put them in the different places. And then now, if you put alpha on the left-hand side, now they are isomorphic. So then you can just write this thing. And then now, we want to introduce the eta function because that will introduce the mempty again. So we write mu as this thing now, which is, well, you cannot write this, right? Because Haskell will not allow you to like better mention a function. However, this is just for introducing the idea of what this is, right? So let's read this carefully because the Tetris here is kind of getting out of hand. So we have a pair with the unit and x. If you apply eta to it, by map eta to the unit, you're gonna get mempty, right? X, and then identity on x. So this means that you're gonna have something in x, but this is saying that whatever is on the left, we ignore it and we just pick the second, and then you just do the opposite for the first guy. So you reverse the ID with the eta, and then these two things will return you x, but they are written in different ways. So we are giving them different names. So this is lambda and this is rho.
And of course, they had to pick lambda because no risk of confusion.
The isomorphisms lambda and rho are called the left and right unit, respectively. They witness the fact that the unit is the identity of the Cartesian product up to isomorphism. So these are basically the implementations of the thing. So instead of using eta now, we're just going to use this. And they are basically doing what I just explained. So then we can replace this entire thing with this and this entire thing with this. Cool. We have formulated point-free monoidal laws for mu and eta using the fact that the underlying Cartesian product itself acts like a monoidal multiplication in the category of types. Uh, the underlying Cartesian product itself acts like a monoidal multiplication in the category of types. What is the monoidal multiplication? The pair?
Yeah,
Okay. Keep in mind though that the associativity and the unit laws for the Cartesian product are valid only up to isomorphism. Sure.
I mean, it's in the name, right? It's a product type.
Yeah. It turns out that these laws can be generalized to any category with products and a terminal object. Categorical products are indeed associative up to isomorphism, and the terminal object is the unit, also up to isomorphism. The associator and the two uniters are natural isomorphisms. The laws can be represented by the commuting diagrams. So let's read this
Eh,
very carefully. This is a product, right? This is a product of twice, so we have two pairs. We have a pair of A and a pair of A and A. And then we bimap that thing with this thing. And we're going to get to this. And then we map this, and we're going to get this. And the same can apply by reversing the me and the ID. Right. And alpha
yep.
is this alpha up here. Cool. Notice that because the product is a bifunctor, you can also lift a pair of morphisms. Yeah, we know that.
There's a tiny detail missing though. Alpha actually has an inverse,
It does have an inverse, which is not the same as alpha.
which is not the same as alpha, yes.
It does have an inverse though. Cool. We could
By
stop
the way,
here. Go.
that diagram is an upside down house.
Yes, it is an upside down house. We could stop here and say that we can define a monoid on top of the category of categorical products in a terminal object. Okay, so let's backtrack a little bit. So what are we doing? Because that may be confusing. We are rewriting the monoid type class, and instead of using the interpretation that we are mapping elements to functions, elements to morphisms, we are mapping pairs to elements, by anchoring this thing. That's what we are doing here. And then we are trying to establish what are the pieces for me and Neta, basically. Because we saw them up here. We saw them up here. So that's what we're doing. And I know that's a lot to grasp, but well, the book is trying its best, I guess. Cool. Uh, as long as we pick an object M and show morphisms me and eta that satisfies monoidal laws, we can have a monoid. But we can do better than that. We don't need a full-blown categorical product to formulate the laws of me and eta. Recall that a product is defined through an universal construction using projections. We haven't used any projections in the formulation. And then we go to a special case of the bifunctor, which is a bifunctor behaves like a product without being a product. Is called a tensor product. And that's the thing. What are we calling behaves like a product?
Basically, it needs to follow the laws of associativity and identity.
Okay. Um,
Like you could apply this to some types actually, using void as the identity as well.
mm-hmm. So we're going to call this bifunctor a tensor product, often denoted by this infix operator. A definition of a tensor product is general, but we're not going to worry about it. In general is a bit tricky, but we're not going to worry about it. We just list its properties, and most important being associativity up to isomorphism. And then similarly, we don't need the terminal object because as you recall, we use the terminal. Well, we didn't use it per se, but it's kind of like it's in here. It's in here. Cool. Then uh, we never use this terminal property, which is that the existence of a unique morphism from any object to it. What we require is that it works well in concert with the tensor product, which, well, we use it, right? So the tensor product, which is the bimap in this case, the bifunctor, we use eta, but we didn't use the fact that it is a terminal object.
Yep.
Yes. We just used, well, yes, we didn't use that fact. We didn't use that fact. That's true. That is true. So it could be anything in here.
Yeah, it needs to work well with the tensor type, right? In this case, the unit makes sense because it allows you to fill an empty spot in a pair without actually adding any information, essentially.
Yeah. Okay, cool. And again, I don't know if I 100% understood the consequences of that, but let's move on. Because I understand that we didn't use this fact. That is correct. Which means that we want it to be the unit of a tensor product again up to isomorphism. Let's put it all together. So a monoidal category is a category C equipped with a bifunctor called the tensor product. So you have a pair and you go, well, we have a pair, a Cartesian product, you from elements of the C category, and you go to another element of the C category. And a distinct object I called the unit object together with three network isomorphisms called respectively the associator and the left and right unitors. So this is the associator thing, which in this case is this, right? I guess.
The associator is actually alpha, I think.
No, that is correct. The associator is alpha. Actually, it's written. This is the associator. We need something that picks the distinct object, the unit object, and any object from it, and gives us it back. And the opposite. So that would be lambda and
Lambda
rho.
and rho. Yeah.
Okay. There's also a coherence condition for simplifying a quadruple tensor product. I didn't understand this, but I don't know if it's worth talking about it.
That would be a product where each element itself is a product.
Ah, I see. I see. I see. I see. What's important is that a tensor product describes many familiar bifunctors. In particular, it works for a product, a coproduct, and as we see shortly, for the composition of window functors. Uh, Monoidal categories will play an essential role in the formulation of enriched categories. Cool. Okay, so all of this, again, always good to make a summary. All of this is because we want to be able to use this new definition of the monoidal category with a monad. That's what we want to do. And all of this to understand a meme. So it's kind of expensive, in my opinion.
Yep.
All of this to understand a meme. So let's go. Uh, so we're now ready to define a monoid in a more general setting. Let's start by picking object M. Using the tensor product, we can form powers of M. The square of M is M tensor with M. There are two ways of forming the cube of M, but they are isomorphic through the associator. Makes sense. Similarly, the higher powers of M, similarly for the higher powers of M. To form a monoid, we need to pick two morphisms, which is mi and eta, again. So if you take a look very closely, if you take a look very closely to these notations and the ones all the way from the beginning, this was capital I and T. This was T of T, uh,
It was t squared,
T
t after
square,
t.
and going to T.
Yep.
So again, the parallels in here, the parallels. And there's another difference. These are morphisms. The other things were natural transformations. So there's also like an existential plane difference, um, where I is the unit object for a tensor product. Cool. These
And then there's the
morphisms.
mandatory Lord of the Rings reference for some reason.
These morphisms have to satisfy associativity and unit loss, which can be expressed in terms of the following commuting diagrams. This is the same diagram that we saw before. This is the associativity law, and this, I believe, these things down here is the unit law, right? The whole, the lambda, and the whole.
Basically, yes.
Cool. And then there is this thing. There is this thing. So let's take a look. If you pick the unit object and the object M with the tensor product, and you apply eta and identity, you're going to go to MM.
Yes.
And then you can ask yourself, does this make sense? The answer is yes, because uh,
It's literally just a bimap.
yeah, but it is kind of weird that we are using tensor product in the blue things.
That's the bimap bifunctor. Like that's the mapping operation over this bifunctor,
No, I
basically.
understand what it wants to tell me, but the notation is not great. Do you agree with that?
I
Because
agree, but it is
this is saying pair and this is by map.
I agree, but this is consistent with how it's been throughout the book, so
No risk of confusion.
no risk of confusion indeed.
Okay. Okay, but it, putting in real terms, this symbol is not the same as this thing. Because this is making a product and this is by mapping it, which is different.
Yes.
And then it makes sense that from this to M, you just apply lambda, and from this to this, you apply ho, and from this to this, you just apply mi, which is joined.
And
And
and there's some deeper meaning here because this is the same diagram that had you confused earlier.
no, yeah, but now I wonder if I was confused because of the same problem, notation.
Yeah,
Uh,
probably.
uh, because in there
Probably.
I noticed. So, okay, so what is the meaning of decompose? This is just
That's
functor composition then.
functor composition, yes.
And this,
This is a natural transformation horizontal composition.
uh, oh, so then that was why I was confused. These are not the same composition thingies.
They are not, yes.
Okay, so yeah, I have very many critiques about notation on this book. Uh, But that's cool. Notice that it's essential that the tensor product be a bifunctor because we need to lift pairs to form products such as this and this. No, these are not products though. Again, I am confused. These things are not products. Am I right or am I wrong?
They could be if this was an applicative bifunctor.
They could be. But this is a bi-map, right? What is written here is that we are bi-mapping this guy with this.
Yes,
So this is not a product.
it's not an actual product, no.
So, man, fuck. Okay. These diagrams are just a straightforward generalization. Cool. So now, yeah, so we are 2 pages and we have 10 minutes. Monoidal structures pop up in unexpected places. We know that. Um, if you squint a little, you'll be able to see that functor composition as a form of multiplication, which I haven't got to that point yet. The problem is that not any two functors can be composed. The target category of one has to be the source category of the other. That's just the usual rule of composition morphisms, and as we know, functors are morphisms in the category cat, makes sense. But just like endomorphisms are always composable, and we've seen this before, right? That's why we can do the t-square.
Yep.
Endofunctors, for any given category, C, endofunctors from C to C form the functor category CC. Its objects are endofunctors, and morphisms are natural transformations between them. We also know that. We can take any two objects from this category, say endofunctors F and G, and produce a third object, which is, yeah, so in this particular case, we are creating objects by composing things. We are creating
Yep.
objects by composing things. Is endofunctor composition a good candidate for a tensor product? That's a very good question, right? That's a very good fucking question. First, we have to establish that it's a bifunctor. Can it be used to lift a pair of morphisms here, natural transformations? The signature of the analog of bimap for the tensor product would look something like. So you have a function, a morphism, and then another morphism, and the result of that is making a product from the two
It
the
takes
two objects that you received for these two morphisms.
not quite. It makes a morphism that takes a product of the source types of the two morphisms to the destination
Yeah, but
types.
we're going to implement them by grabbing the elements, right? We're going to do some lambdas and then put them at the end using this thing. That's
Basically.
how I read it. And the same for the other two things, so B and D. If you replace objects by endofunctors, arrows by natural transformations, and tensor products by composition, so this is kind of insane if you think about it, because there is a natural transformation from F to F prime, and there is a natural transformation from G to G prime. And what are we doing with them is composing F with G, and that is a first element to get the composition of F prime with G prime. So this is kind of insane within itself. And then you can read it as this thing, right? So if you have an F, and then you are applying G to it, so this thing, F after, wait, wait, do I understand this? This arrow makes sense, which is this arrow, so it's this one. This arrow is this one, and the end result.
For some reason he decided to flip the F and the G here, but okay.
Okay, so that is a typo then. The arrows are reversed. The horizontal ones, I mean.
Yeah, because if you stick to the usual meaning of the dot being after, right? F
Yes,
after G, that's not
yes.
what this diagram is describing.
Okay, so another typo. Maybe we should do some issues on the repo. Maybe. But maybe nobody cares because there is another book that he wrote that apparently is the like a bigger dad than this one. But okay. We also have at our disposal the identity functor I, which can serve as the identity for endofunctor composition, our new tensor product. Moreover, functor composition is associative. In fact, associativity and unit laws are strict. There is no need for the associator or the true uniters. Yeah, now we are dropping the alpha, the whole, and the lambda because functor composition is associative. So endofunctors form a strict monoidal category with functor composition as tensor product. What's a monoid in this category? It's an object. That is the an endofunctor T and two morphisms. That is natural transformation. So now we went back to where we started, right? So we are just establishing that a monoid in this strict monoidal category is has one object, right, which is an endofunctor T, and these are its available natural transformations.
Yep.
And this is representing mappend, and this is representing mempty.
Yep.
Not only that, here are the monoid laws. So again, the same diagrams from before.
Yep.
And now, after that, we can say that monad is just a monoid in the category of endofunctors.
Amazing.
I heard that this is just like really depends on your definitions of what those terms mean, because the course that I mentioned to you, right, the IOHK course, the IOG course, the teacher said that the definitions that we would use would not conclude this. That this would be like an error in the terminology.
I
But
see.
according to this book that we are using as reference, it does make sense.
Yeah, it depends on which meanings you assign to each symbol, right?
Yeah. So now, 5 minutes, we are going to talk about adjunctions. So this is just an explanation on how you can derive monods by using adjunctions. So then we go back to the adjunction, go back and forth between C and D, all of that conversation about equality and equivalence, how that is hard, and that's why we use adjunctions, because that we at least we have a better understanding of what they mean instead of just talking about equality in a general sense. And then we go back to these guys, which are basically establishing the equality of adjunctions by putting as the equal member. So to establish that they are equal is to use the identity natural transformation. And then it turns out that R after L adjunctions, they are indeed form a monad. Uh, and then you need to define the appropriate mi and eta, and its natural transformation between the squares of endofunctor and endofunctor itself, or in terms of the adjoint functors. So I don't recall. Why are we doing this operation?
Because that's the output of eta squared.
This is the output of eta squared. And why are we doing eta squared?
Because we're trying to define mi, which goes from eta, well, it goes from the square of the monad to the monad.
Oh, we are picking our T is R after L.
Yeah,
Oh, so okay, so this is, but we have a trick because we can use
sigma, I think.
sigma in the middle here. So it goes to
Is it?
this. I don't think this is
Is it?
sigma though.
I don't think. No, I made
Epsilon.
a mistake. Yeah, that's epsilon. Yeah. Um, Greek alphabet, I don't actually know it. I just absorbed some of it from osmosis.
That's fine. And indeed, you can use the co-unit to collapse, as I already said. Monadic laws follow from the identity satisfied by the unit and co-unit of the adjunction and the interchange law. We don't see a lot of monads adjunctions in Haskell because an adjunction usually involves two categories. Remember, C and D.
Yeah.
And monads are monoids in the category of endofunctor, so we don't have a D. Well, we do, but D is C. Um, so, however, the definitions of an exponential or a function object is an exception. Here are the two endofunctors that form this adjunction. So, as far as I can tell, this is the two endofunctors that form the adjunction, which is the exponential. Is that what's being said here?
Yeah.
Wait, it's saying a functional object. So this is a functional. This is what it's calling a functional object.
Basically, yes.
So you may recognize the composition as a familiar state monad. So if you put B in the place of B this guy, You're gonna get this, which, not surprisingly, it's the state. And not even less, well, less, I wouldn't say less surprising, but the same amount, you can rewrite state using prod and reader. The left functor is the product functor. So this guy, which is basically so putting the reverse order of this in a tuple.
Yep.
And the right functor is the reader, which is basically just putting a function in the middle. And they form an adjunction. So here's the unit. I don't remember which one is called unit again. This? Yes.
I think so, yes.
So the unit needs to go from an element A, right? So yeah, this is how you do it. This is 100% how you do it. And co-unit needs to pick their composition. So you're going to do pattern matching probably. Yeah. And you need to go to identity on C. Identity on C. So this is C then. And the other one I need to go to identity of from identity of D actually. So
It's just
D,
that in this case, C and D are actually the same.
no, they aren't. I
In
don't think
general,
they're.
they aren't, yes, but in this case, they happen to be.
No, but I don't follow what you said actually because oh, they are the same. You said they are the
Yeah,
same. So it's also
because you're
A.
yeah, because you are
Yeah.
starting in the universe of Haskell types, and you are following through eta and then epsilon, and you are coming back to the universe of Haskell types. So they happen to be the same, but in general they aren't necessarily.
Okay, no, that makes sense. Yeah, no, this is also doing A twice as the thing. You can easily convince yourself that the composition of the reader functor after the product functor is indeed equivalent to the state functor. So we need to compose the functors. I don't remember how to do that in Haskell though. Do you remember?
That's just applying one functor after the other, no?
Yes. Yes, no, this is just F mapping twice.
Yeah.
Cool. As expected, the unit of adjunction is equivalent to the return function, and the co-unit acts by evaluating a function argument on its argument. This is recognizable as the uncurrent version of the function state, run state. So you have a state and you have an S. You grab the function from state, which is this function. You have an S, you just apply that to it, and you're gonna get this. There are many things that have runnable functions. So run state, run reader, and so on and so forth. And that's gonna be important to implement the other things. So yeah, I think this type Tetris is really hard, but I will try my best to explain it fast. So, well, fast and like, understandable. So we want to implement join. That's kind of the goal. We want to implement join and return. Unit is the definition of return. So is this thing. Now we need to take care of the join. The co-unit acts by, yeah, so we're gonna use run state as an auxiliary piece to make it. We can now define join for the state one as a component of the natural transformation me. Yeah, no, but we've seen this before. We've seen this before because L is the left, is the product. Then we are using the epsilon here, right? So me needs to pick an m of m and return just an m. So we know that L is this functor here, and this is the right one. And then, so that's how it's gonna go. Quite literally the same thing as before. So we need to sneak the co-unit epsilon across one level of the reader functor. We can't just call fmat directly because the compiler will pick that one for the state functor rather than the reader functor. So let's backtrack a little bit. Let's backtrack a little bit. So how to explain that? Uh, ah, Wait a moment. Marinho, help me.
Hmm.
So we can just call fmap directly, right? What is this? Is product and this is reader, right? Are you there?
Yeah, reader is outside of product. Hmm.
Yeah. So if you apply L, we're gonna apply the product the prod functor, right?
Yeah.
So the prod functor will pick something and put it into the prod, right? That's what it's going to do. This.
Yeah.
Cool. Why can't we apply epsilon then? Yeah, because here kind of makes sense. Because we are grabbing the t square. But where are we gonna get this thing?
That's just um that's just run state, no?
That's just run state, you said. You're saying that epsilon is run state?
Mm,
Like here, the
e-
Tetris makes sense. But what is it? What is epsilon in our case?
I think if you go down a little bit more, let's see. We sneak. We need to sneak the co-unit epsilon across the reader function. We
Oh,
can't.
okay, I understand. Okay, so epsilon is a function that picks the state already. It picks this thing.
Yeah.
But okay, so what's coming is actually a reader then. We grab the reader, apply L to it, which is going to wrap it into a prod, apply epsilon to it again, get rid of it, and then apply R to it. R is the reader, which is exactly this, right? We
Yeah.
can't just call fmap directly because the compiler would pick that one for the state functor rather than the reader functor. But recall that fmap for the reader functor is just left composition. So use function composition directly. We have to first peel off the data state to compose. Okay, so this is an M of M. This is the t square.
Yep.
Um, and then if you apply this thing to run state, which is the t square. Yeah, Marinho. Okay, so you're okay. So what's coming to apply the me is actually SSA. We know the definition is going to be this, but what's going to be the implementation? So it's coming this thing to here. So we first call run state on top of it, and that will grab the outer one, the outer state, unwrap it. That will give us a function. That will give us a function um, in which the a value is another state. So we're gonna grab the function and apply s to it. So we're gonna apply this thing here to the function. But this is a function that will give us another state. This, right? Then we left compose it with the co-unit, which is defined by uncurry run state. So this is why I think the type Tetris is kind of hard, because how do you read this? Because this is going to be this thing.
Well, you read this as join of SSA equals state of the uncarried run state after run state of SSA. That's how you read it.
Yeah. So let's try to go a little bit slower here. So we are trying to grab two states and return a single one out of them. So we want to like combine them in a way. Uh, State needs to receive a thing. It needs to receive a thing. So if you go to the definition, it needs to receive a function. It needs to receive a function. So this is a function, which makes sense. Now let's read it from right to left. You grab the thing you pass it to run state. This will be the output type. Okay, so this is the S from here. Now
Yep.
we need this pair, right? We need this pair. So how are we gonna do it? It's from here. So we are grabbing, this is gonna be fixed, and then we need that this transforms to S of A, SA actually, S comma A. How are we gonna do that? We're gonna grab that and apply this function to it. What is this function? This function is run state, which is this thing, right? Run state,
But
but we
it's
are,
uncurried.
yeah, and then we're gonna uncurry that thing. So uncurrying it will make the result of this, the result of this to be a pair. Agree?
Uh, no, actually, it's going to make a pair of the two arguments.
Oh no, you're right. It's gonna pick this thing and make it into a pair.
Yep.
And that's exactly what we have. That's
Yep.
exactly what we're gonna provide to it. So if you uncurry this thing, it's gonna put instead of a well, an arrow here, it's just gonna be a pair, which is exactly what we need. Which means that now we're gonna have this on hand, which means that it's a function from S to this thing, which is exactly the lambda that we need to make a state. And that's why it works, and it is hard, and you need to practice a little bit of the type Tetris. It turns out that not every adjunction gives rise to a monad, but the converse is also true. Every monad can be factorized into a composition of two adjoint functors. Such factorizations are unique though. We talk about the other end of functor LR in the next section, which is the comonads. Which is the comonad. So let me explain. This me thing is the join.
Yep.
And I would like, Marinho, can we identify in the implementation which part is which from here?
Let's see. Well, let's go from left to right because that's the order that it's written in. The R is just the state constructor, right?
No, but R is the reader, right? It's saying here. The right functor is the reader functor. So
The
R
right
must be
functor
the
is the
reader.
reader functor.
Yeah, we are composing functors. This is a composing functors.
All right, the output of this needs to be a reader actually. Hmm.
No, but it is a reader. State is a reader.
State is a reader indeed.
But I want to identify, well, I want to attempt to identify in the implementation each section of this. I'm having a hard time, not gonna lie.
Hmm. Hmm.
Which part is prod, which part is counit, and which part is reader? That's kind of,
You mean reader, right?
yeah, reader. Reader, prod, and counit.
Well, state is the composition of reader after prod, right?
Yes.
That means that state actually is the reader in this case. So that is
Yes.
CR. Uh,
Wait, so this R is this?
yes.
Cool. And what is the epsilon?
The epsilon is the uncurried run state,
This thing.
I think. Hmm.
So let's see why. The epsilon is the counit, correct? So it's this.
Uh, yes.
So what? So you said that it is the uncurried run state. Are you sure? Because if you uncurry this, it's going to be a pair to a pair, right?
Right.
Is this this?
Well, assuming f returns a pair, then yes.
No, but F does return a pair.
Then it is in fact.
And then the L is gonna be this thing then.
The L is just the run state, yes. Well, actually, no, it's the output of running the state of SSA, right?
So L should be the prod part. Oh no, but the prod and reader functors is the state.
Hmm.
Is the state. I need, yeah, because there is a difference, right? In here, these are types, but we are using them as not the same name for their functor versions.
That's because they are isomorphic, right?
Well,
The
yes,
two
but
constructions. Yeah.
that you need to pay attention to that because reader and prodder functors, they are types and roles because the state is the reader and the state is the prod.
Yeah, the prod and the reader are like parts of the state.
Yeah. Um, okay, and then the L, which is the thing about the prod, is the run state thing. So the run state. Okay, so there's no really relationship between this thing and this thing.
Between this thing and this thing.
Yeah, I'm trying to understand because it says the left functor is the product functor, but this is a type.
Well, yes.
So, and then we are trying to identify this is a functor. Cool. Which part of the code represents the L? We established that it is this thing, but this thing is this type, and this has nothing to do with
Uh,
product, right?
which part is the L? Well, run state takes a state. Hmm,
Oh no, it is this actually because this is the product.
that's the product, yes.
Ah, this is the product part of it, and the reader part of it.
Is the fact that the output is in fact a function.
Yes. Okay, okay, we did it. Did it. Okay, okay. We won. We won the battle. Cool. I'm gonna finish the recording now.
By future people.
Bye.